In this lesson, we will learn how to use exponential functions to model and solve real-world problems. Now, with that, every application of exponential functions in the real world can either be classified as either exponential growth or exponential decay. So, special cases of exponential growth include something dealing with doubling. Doubling is the time it takes for a quantity to grow or increase to double its initial amount. So we often use this function notation to represent exponential function situation where we have some doubling occurring. So d at t is equal to d subscript 0. 2 would be your base for this exponential function because we are doubling all to the exponent of t over d. Now, d at t is that final amount. D subscript 0 is the initial amount. T is the time, and D is that doubling period. How long does it take my product to double? So we have, let's look at example 1. A certain type of bacteria doubles in population every 3 hours. So then the base would be 2, and the doubling period is 3 hours. If the initial bacteria is 1,000, determine the size of the culture after 2 days. You're observing this bacteria over 2 days. We know every 3 hours, the population doubles. So let's use that function notation there and break down the information. So we know d at t, that's what we're trying to figure out. What is this population after 2 days? We know that the initial population, which is 1,000, we know the time we're observing is 2 days. However, because the doubling period is in terms of hours, so D is equal to 3 hours, we need to convert the days to hours. So we know there are 24 hours in 1 day. That means we're looking at this bacteria for 48 hours. So T is 48. Now the time is the same. You have to make sure you always have those same units. So substituting, we'd have D at T is equal to initial population, which is 1,000. The doubling represents a base of 2, all to the exponent of 48 over 3. So T over D. Simplifying, always following BEDMAS. 48 divided by 3 we know is 2 to the power of 16. Again, always following BEDMAS, we deal with 2 to the power of 16, which would be 1,000 times 65,536, and we multiply that by 1,000, 65,536,000. Okay, and because it is a word problem, we didn't round anywhere. We're going to say, therefore, the size of the culture after 2 days is 65,536,000 bacteria. Again, anytime it says doubles, that base of your exponential function would be 2. 2 represents that doubling. That's pretty important. Okay, another form of exponential growth that we see is money. Okay, the compound interest, when you're looking at that formula, that is an example of an exponential function. So amount at n is that final amount. P subscript 0, again, 0 represents that initial point, the starting point, time is 0, so is the principal amount. I is the annual interest rate, and n is the number of years. So the formula A at n is equal to the initial amount, principal amount, P at 0, times 1 plus I, all to the exponent of n. Okay, and in this case, it is money invested or compounded, and the compounding periods can vary. Keep in mind, annually is 1 time a year, semi-annual would be 2 times a year, quarterly would be 4 times a year, monthly would be 12 times a year. Right? Weekly, there's 52 weeks in a year, bi-weekly would be 26, half of that, and daily would be 365. So looking at example 2, we're going to use that compound interest formula. That is an example of exponential growth. James has 2000 to invest in a compound interest account that earns 8% per annum compounded annually. So I'm just going to highlight that. So compounded annually means once a year. Okay, so that means, and we usually denote that as capital N, compounding periods. Determine the value of his investment after 4 years. Okay, so we're going to break down because we do have the formula in front of us. The final amount is what we're trying to determine. So that's our unknown. We know what our initial amount is, which was $2,000. Okay. The interest, we always take the interest and convert it to decimal, so 8%. And by doing that, we just divide by 100%, which is 0.08. So with interest, we always take the rate divided by the compounding periods. So in this case, it's 0.08. Compounded period is 1, but if it was, say, semi-annually, we divide it by 2. If it was quarterly, we divide by 4. So in this case, annually doesn't really impact. Right. And then, of course, you always take the years. So you take compounding period times your time, your years. So n is going to equal to 1 times 4 because we're there for 4 years. So n is equal to 4. Okay. So now substituting into our formula. 4 is equal to initial amount of 2,000. 1 plus my I, which is 0.08, all to the exponent of n, which is 4. Again, always following BEDMAS brackets first. So we're going to take 2,000, 1 plus 0.08 is 1.08, all to the power 4. Next would be exponents. And then, of course, we can multiply. So it's going to be, we round and money to 2 decimal places. Okay, so after 4 years, we can say, therefore, the value of James's investment is $2,720.98. Let's say about because we did round there for me. Excellent. Okay, so those are my special cases for exponential growth. Unfortunately, there's also exponential decay. So half-life, this time the base is not 2 for doubling, it's half-life. So half, think of 1 over 2. So half-life is the time it takes for a quantity to decay or to be reduced to half its initial amount. So typically we use this exponential formula, which is m at t. So the initial final amount, is equal to m subscript 0, which is your initial amount, times the base 1/2 to the exponent of time over the half-life period, which is h. Or how long does it take for half the material to be reduced? So let's look at example 3. We have radon has a half-life of 25 days. How much time will it take for 1,280 grams radon to decay to 10 grams? Okay, so again, we want to know that final, this time it's a little bit different because we have that final amount. So we're going to say m at t is equal to 10. My initial amount we know is 1,280. We know the time is 25. We want to know, the half-life, I should say, not time, half-life, sorry about that. Half-life is 25, and we want to know what the t is. And by using our formula, m at t, so 10 is equal to the initial amount of 1,280. Base of 1/2, all to the exponent of t over 25. Okay, so we want to get the exponent by itself. The first thing we want to do is get rid of this a value up front. So we're going to divide both sides by 1,280. That will get rid of that. And if we simplify that and divide both of those by 10, we're going to just leave it as a fraction, is equal to 1/2 to the exponent of t over 25. Now, remember when we were solving exponential equations, we want to be able to express 128 as a base of 2. So, or 1 over 128. When I say 1/2 to the exponent of 7 would equal to 100 over 128. So we're going to say 1/2 to the power of t 25. So now that the bases are the same, using our knowledge of solving exponential equations, we can say therefore the bases are the same. That means these exponents have to be equal as well. So 7 is equal to t over 25. And then we can bring the 25 over there. So we're going to say t is equal to 7 times 25. T is equal to 175 days. So therefore, it will take 175 days for 1,280 grams of iron to decay to 10 grams. Another example of exponential decay is the depreciation of assets. A car is very famous for this, right? A car depreciates as soon as you drive it off the lot. So depreciation of assets, we can use this notation, which is often used. V at n is equal to V initial times 1 minus r all to the exponent of n. V at t is that final price. V subscript of 0 is the principal value, so the initial amount. R is the rate of depreciation. N is the number of years the asset has depreciated. So looking at example 4, we have an ancestral mansion built 100 years ago, had a value of $995,000 during its glory days, but the property has since been abandoned and was left unmaintained during the Great Depression. The mansion depreciates at a rate of 10% per year. What is the value of the mansion now? Okay, so we already have the initial value, which is 995,000. We know it depreciates at a rate of 10%. So 10% divided by 100, which is 0.10. And we know we want to observe how much it is now, which 100 years have passed. So V at 100 is going to equal to the initial amount, 1 minus 0.10 all to the exponent of 100. That's very critical. Again, always following BEDMAS. So that makes sense. Each year, if you're losing 10% each year, you're left with 90% of the initial amount. Now, again, always following BEDMAS. 0.92 exponent of 100. Let's calculate that quickly. 9 to the exponent of 100. It's going to be 0.00265. 6139889, and we're going to multiply that by 995,000. Oh boy, the 100. If it depreciates at this rate, it's going to be $26 and about 43 cents. Because remember, we always round to 2 decimal places. So therefore, the value of the mansion now is, of course, if it depreciates at 10% per year, would be as about, I should say, $26.43. Okay, so just to summary, exponential growth and decay, the functions f at x equals a times base b to the exponent of x can be used to solve exponential growth or decay problems. Exponential growth, example of that, again, would be the doubling time or compound interest. Exponential decay would be half-life or that depreciation of assets.